Good morning, everyone. Thank you so much for joining me today here in the Madison room. My name is Brad Miro. I'm an engineer at Google working in developer relations. A lot of the work I do focuses on the open source technology that we offer as a part of Google Cloud, specifically in the machine learning and big data spaces. So today I am here to talk to you about distributed machine learning with Python. So before I dive in, I would just love to get a show of hands here. Who has done machine learning at all in any capacity, even as much as that? Wow, that's great. Who here has done machine learning on anything other than your laptop or your local workstation? Okay, cool. That's super awesome. So we'll dive in, and some of this might be familiar to some of you already, which is great. So just to give you an idea of what we're going to go over today, we're going to start with just an introduction to what distributed machine learning is, as well as go into some of the history. We'll then discuss some of the hardware considerations that you have to think about when you're actually building your distributed machine learning clusters. We'll discuss some paradigms and different ways that you can actually go about distributing your machine learning training fundamentally. We'll then discuss some software considerations, and then we'll just have some closing thoughts to wrap up the talk. So with that, we'll just dive right into distributed machine learning. So there's a history of distributed machine learning as there is anything. I like to start talking about it around 2004, beginning with MapReduce. MapReduce being a framework for doing just distributed parallel processing across multiple machines that just made this much easier than anything to do at the time. In 2006, we were introduced to Hadoop, which is another piece of software that allows you to do distributed computing as well as have distributed file storage and something called HDFS. In 2009, Mahout, people disagree on the pronunciation, but Mahout was introduced, which introduced scalable machine learning in the form of scientific computing, and that was actually built on top of Hadoop. And then in 2012, we were introduced to a paper that introduced a framework called Disbelief. And so that was written by Jeff Dean of Google, as well as several others. In 2014, we had Apache Spark, which is an in-memory data processing framework that has machine learning capabilities. And then in 2015, we were introduced to TensorFlow, which was actually developed heavily based off of the findings from the Disbelief paper that Jeff Dean and his team worked on. And then in 2016, another big breakthrough was the introduction of the TPU, or the Tensor Processing Unit. So Spark, TensorFlow, and TPUs we'll actually discuss later on in the talk, so I won't go too far into them right now. So when we talk about distributed machine learning, I think it's good to start by talking about what machine learning on one machine looks like, or just using your laptop, or just your desktop, just a single machine. So generally speaking, machine learning is hard. It's 2019, so we have a lot of functionality and pieces of software that can abstract a lot of the difficulties and a lot of the mathematical computations away from you. But fundamentally, what's happening under the hood is a lot of really advanced linear algebra and statistics and things that people don't necessarily have the expertise or interest in learning about. And so I mentioned one of those is linear algebra. So computationally, linear algebra is very expensive operations. Has very expensive operations. Linear algebra being the branch of mathematics that deals with doing computations on matrices. Matrices being two-dimensional pieces of data. For those of you who have, we've all used a CSV file. If you load a CSV file into memory, that is effectively a matrix with rows and columns. And optimizing computations on those is actually very difficult, especially just to do synchronously on a single machine. Another problem with using one machine is that large models, and when I say large, I mean models that have millions or billions of parameters or weights associated with them, oftentimes those are larger than the available RAM that you have on your computer. And we don't want to use swap either, because swap is obviously extremely slow. So sometimes the models that you're working on or that you want to work on just won't even fit onto your machine. And then if you have a lot of training data, that could also be time consuming to load everything into memory. Even if you're doing it using loading in batches at a time, you could still have so much data that your model could still take days, weeks, months, or even many, many years to train. So that's obviously not reasonable. And then what happens if your machine crashes? What if you just have hardware failure on your single machine? You might end up just losing all the training that you're working on, especially if you've already put hours or days or even longer into actually training your model. But then if we move on to multiple machines, we're able to take advantage of the fact that things such as linear algebra are parallelizable. you can also take your large models and then split them across multiple machines. You don't have to necessarily be confined to the one machine that you have, and you can leverage the new pieces of hardware that you're introducing. Additionally, you can, there's ways to process your training data in parallel. So if you have 4 machines, there's actually ways that you can take all of your data and process approximately a fourth of it on each one of those 4 machines, or 1/n of the data for n machines that you may have. You can also introduce fault tolerance so that if one of your machines crashes, then you can have replication or ways to actually continue training without significant, or in a lot of cases, any data loss or loss of any training. And the goal here is that by introducing machines, we're looking for near linear additional performance per machine. In reality, that isn't exactly what happens, but we can usually get pretty close, especially if we're working with software that's been optimized to handle the additional machines. So, but why do we really care? Why are we interested in these large models or using lots of training data? So the reality is that larger models are often better for what we call complex problems that typically deal with unstructured data, or at least these are the more commonly seen use cases. And those include audio, images, and text are 3 of the big ones. There's many others, but you tend to see these the most frequently. And then a lot of these models can also often benefit from having all of this training data. So if you have terabytes of training data, or even just on the order of hundreds of gigabytes of training data, it's usually the case where you're going to want to benefit, your model will benefit from training on all of this data. So you want to figure out ways that you can most effectively use these to creating better models for your use case. But that being said, you definitely shouldn't always distribute, and there are potentially drawbacks to doing so. So as I was mentioning earlier, there is some overhead involved with parallelization, and if your models are too small or if you have too little training data, it could actually take more time to distribute it than it would if you just trained it on your laptop. So that's very use case specific, and sometimes you'll have to just honestly experiment to see which works best for you, but something to keep in mind. And then also a lot of ways to parallelize actually rely on all of the machines having roughly similar computational power. So you might have limitations based on I/O from older machines. So there are definitely things to think about here. And just because you can distribute doesn't mean you necessarily should. So when you're figuring out if you need to actually build out a distributed cluster, some things you need to think about. Obviously, do you really need this? Will you expect that you might need this in the future, even if you don't now? And ways that you could think about that are in terms of if you have a lot of data currently, do you expect that you'll have a lot of data? If you're a new company and you might have a lot of data now, but a year from now, your data may multiply by several factors. So these are things you need to think about, as well as the types of models that you're going to be working with and the domains the domains that you're also going to be working with, to see if these are things that you'll actually need to think about. Okay, so that was just a general introduction to distributed machine learning, and now we're going to talk about some pieces of hardware, or the pieces of hardware that are actually involved in this. The first one is something everyone in the room should know and love, the CPU, the central processing unit. So these are in every one of your laptops, all of your computers. And they were really designed originally for general purpose programming and for a wide variety of use cases. We all know CPUs can handle effectively anything you can throw, anything that you can throw at it. But the idea is that these were designed for single-threaded operations that happen synchronously. So if you have just a single CPU or even a couple CPUs, it's actually very difficult to optimize for things such as linear algebra and other things that machine learning computations tend to look like. But of course, as with CPUs, you can utilize multiple of them to achieve greater performance. But for actually using, for hardware that's actually much better tailored towards doing mathematical computations, something that you want to look at is the graphics processing unit, or the GPU. So these were literally designed to do parallel processing. As in the name, they were designed to do graphics rendering for video games and for video playback and things of that nature. But machine learning researchers identified that these are actually really great for doing deep learning and machine learning because of their ability to process linear algebra and matrices really efficiently. So nowadays, a lot of the large GPU manufacturers have shifted their attention away from focusing on graphics to focusing now on machine learning and artificial intelligence. And of course, like CPUs, you can chain multiple of these together to achieve better performance. And then last but not least is the tensor processing unit, also known as the TPU. So this is the newest of the bunch. The first version of this was actually announced in 2016. So TPUs were designed specifically for machine learning. They were built to be used with TensorFlow, which is a piece of software that Google built. And because of that, there was also the TPU itself was also built at Google. So this is Google technology. And the idea here is that they're able to just provide even better performance that GPUs are able to, but they really rely on optimizing very closely with TensorFlow. So if you're using TensorFlow, they're great, but otherwise you might have some issues with compatibility. And like CPUs and GPUs, you can chain multiples of these together in what we call a TPU pods. So if you're deciding which one of these you should be using, there's a lot of gray area here, but the general idea for this is that the CPUs are really great if you're working locally, if you might be prototyping a model that you're working on and just a small subset of your data, just to see if you can have some minimum valuable product. They're also really good for something called a parameter server and your master node, which are things that we're going to talk about a little later in the talk. But you're actually able to, you're not supposed to just use CPUs or GPUs or TPUs. There's ways that you can combine these together. So CPUs end up being really good at what I like to say are the brains of some of your operations, where GPUs and TPUs are really good for doing the mathematical computations. TPUs are best if you're going to be using TensorFlow, and then GPUs are great for everything else and are generally just great overall. So then when you're deciding if you're going to start distributing your machine learning operations, another consideration that you're going to have to think about is if you want to do this on-prem or in the cloud. On-prem being physical hardware that you or your organization is purchasing and managing, actually putting the chips in and providing the power and everything like that. With the cloud being using generally one of the cloud providers such as Google Cloud or AWS or Azure. And so there's pros and cons to both. When thinking about whether or not you want to start doing this in the cloud, something to consider is with the data that is available in your industry, are you even legally allowed to do so? There's a lot of regulations around industries such as healthcare and the financial industry around actually migrating your data to the cloud and processing it there. So you might not even have a choice but to build out your own hardware and purchase your GPUs and purchase your CPUs and manage this yourself. But that being said, I have found that it is easier to increase the size of your cluster if you are in the cloud as opposed to going out and actually purchasing hardware, because maintaining physical hardware can be cumbersome. It can also be fun, but it can definitely be challenging, especially if you're running into quick limitations. You're hitting the threshold of what your hardware can actually do very quickly. It's much harder to go out and purchase a GPU and add it to your machine and wire everything together than it is to just log into your cloud provider and just increase the number of machines from 2 to 4 from a drop-down menu. So just things to think around with, and sometimes you'll have to experiment with both to also just see what's best for you or do a lot of R&D to figure out what, not necessarily a lot of R&D, but just sort of take some time to figure out what makes the most sense for you. Okay. So that was an introduction to some of the hardware components. Now I want to talk about some of the paradigms of actually doing distributed machine learning. So there's multiple ways that you can arrange your hardware configurations, of course. So everyone in the room here who is on, I use Macs, so I like to say if you're not using a 15-inch MacBook Pro, then you are on a single node, multi-core CPU machine. As far as I'm aware, there are not dedicated graphics on any 13-inch MacBook. But for those of you with the 15 inches, you would have a single node, single GPU MacBook Pro. Some of you might actually have 2 GPUs in your Mac. I love Mac computers, so I'm fairly knowledgeable about this stuff. But yeah, so this might be you. But then you can also actually chain multiple of these together. So you can chain multiple machines that have CPUs and GPUs together. So there's different, I guess, configurations you can say of how you can actually arrange the hardware. And so with this in mind, we can then take this and apply it to different paradigms for actually parallelizing your data. So the first one that we're going to talk about two. The first one is data parallelism. And so the concept behind this is that you take your model and you copy it onto each piece of hardware that you have, but you then partition your data across multiple machines. So let's say you have 4 workers. Again, you might provide 1/4 of the data. Each machine might process 1/4 of your data. What these will do is they'll compute the gradients and the weights, and then there's different ways that you can actually have the machines interact with each other to have every machine stay updated. And the 2 ways to do that are through synchronous data parallelism and then asynchronous data parallelism. So if you're looking at synchronous data parallelism, what you'll generally start with is you'll have a master node, which I actually don't have in this diagram here, but you'll have a computer, generates a CPU that's able to manage the workload being sent to all of the different machines. And so in this case, each of these workers will be reading in data from whatever data store you have, if it's cloud or on-prem, whatever. And then what will happen is after each one of these will process a certain amount of data in a cycle, and then they'll update each other. So this is really nice because you're processing faster, but the problem is you actually are relying on each one of the workers to finish its processing before you can move on to the next cycle. So you're really only as fast as your slowest worker, which is why earlier I was saying you can run into issues if you have older hardware. Maybe one of your workers is just a couple years old, the other 3 are newer. You're only going to be as fast as that slowest. But you're still able to parallelize, and this is obviously going to be faster than if you were just doing it on one machine. But a really nice solution to this is to do asynchronous data parallelism. And the way that this works is that each one of your workers is going to be processing data. But once it finishes, it actually pushes the updated weights to what we call a parameter server, and then pulling down the weights, which have updates from the other workers. So the idea here is that each worker can really just process as fast as possible. And once it's done, it'll push the parameter server, pull it down. And then at the end, the parameter server is going to be where all of your weights are going to be living. And here it's a great example of where you might just be able to get away with using a CPU for the parameter server, since you're not really doing any computation there other than just either adding or averaging the new weights together. But you're not doing forward propagation or back propagation, which are algorithms for doing deep learning that tend to be fairly computationally expensive. So the next type of parallelism I want to talk about is model parallelism. So originally, when I was talking about data parallelism, the model is actually copied onto each one of the GPUs in its entirety. But sometimes your models might be too large, and that just isn't tractable. So what you can then do is you can take the model and specifically break it up for certain sections of it and put it on on different machines. So the idea here is if you have, let's say, this is most commonly seen in deep learning. Deep learning being a branch of machine learning dealing with an algorithm called neural networks. So it ends up being a section of layers, and you can kind of see it here on this slide. There's like 3 different sets of dots. And so what you can do is you can actually split those up across multiple machines. And what will end up happening is that you can process different parts of the model in parallel across the different machines. The best way to think about it, or one way that I like to think about it, is an assembly line. So if you're working on, let's say, you have an assembly line for building automobiles. You might have one person that's working I'm not a mechanic, by the way, so bear with me here. You might have someone working on, let's say, the tires. You might then have someone specialized in working on tires, someone specialized in working on the engine, someone working on the interior. And so that first person can put the tires on the car, then they can pass it to the next person who can then install the engine, while the first person can then put tires on the new car. So the idea here is that that the span of knowledge for building a car might be more than one person is able to handle. Again, maybe it's not, I don't know. But the idea here is that you can take advantage of splitting the work across multiple different machines to lead to a faster finished product, or in some cases, just a finished product in general. And one of the really interesting first use cases of this was in Jeff Dean's paper back in 2012, where they built a model across thousands of machines that had billions of parameters. And they did find that actually led to better model performance. So I definitely recommend checking that out, and I'll include the name of it at the end, just so that you can take a picture of it or whatever. So model parallelism. So the idea here is you have data parallelism, you have model parallelism, and when to use which, in my opinion, it's fairly straightforward. If your model can fit onto a single machine, you want to do data parallelism. And if it can't, then use model parallelism. Generally, you do want to strive for asynchronous data parallelism. It does just lead to the fastest performance, and this way you're also able to contain the entire model on a single machine and then train or parallelize your data across your multiple machines. Ideally, you'd love to be able to just train on your laptop, but that's just not feasible for a lot of use cases. But depending on what your use case are, you can potentially strive to do asynchronous data parallelism. Okay, so we talked about hardware, we talked about paradigms, and now let's talk about some software that's used for distributed ML. So we're at a Python conference. This is probably the last room here that I need to be explaining this to. But Python has a super rich ecosystem for scientific computing. Who knew? Python's great. So you have NumPy, Pandas, scikit-learn. There's just a wide breadth of pieces of software out there that you can take advantage of within the Python ecosystem itself. Python is also super easy to use, in my opinion. Very also beginner friendly, and folks who might not necessarily be doing this who haven't used Python can get started doing this using Python. And then also the way that Python generally interacts with these scientific computing libraries is generally as like a front-end API to an engine that might be written in Java, Scala, C++, or something that's a bit more optimized for faster performance. So let's talk about some libraries that have Python APIs. And the first one we will talk about is Apache Spark. So Apache Spark is, this is taken from their website. It's an open source unified analytics engine for large scale data processing. The way Apache Spark works is it will load your data into memory, and it can distribute it across multiple machines and shard it and be able to process it and then bring everything together at the end. It has a really rich ecosystem of tools available to it. One that is specifically used for machine learning is called MLlib, and that's part of the core build of Apache Spark. Spark has APIs available in Python, Java, Scala, and R. So I'll be showing you a PySpark example. And then also the parallelization of Apache Spark. In terms of the actual code itself, the parallelization is abstracted. So when we started working on this stuff, you had to be really specific on where you were distributing your data. So you might have, let's say, you had to load everything into memory, and then you had to say, take this portion of it, process it on this machine, this portion, process it on this machine. When you use Apache Spark, you don't have to worry about any of that. It takes care of everything underneath the hood for you, no matter what the job is. So the Apache Spark ecosystem has a lot of tools available to it. So in terms of the ecosystem itself, you have Spark SQL, which is the ability to actually interact with your data in memory just using regular SQL queries. You have Spark Streaming, which allows you to process streaming data using Apache Spark. You have MLlib for doing machine learning. And you have GraphX for processing graph algorithms. So these four are part of the core build of Apache Spark. One piece of software that isn't in the core build that I feel inclined to talk about is also a Spark NLP, which I cannot remember the year, but Katie Nuggets came out with an article, I think last year, that said that Spark NLP was the most widely used natural language processing library in the world, which is pretty cool, and I've spent some time with it, and it has a lot of really rich features to do distributed natural language processing. Text also being one of the areas today where there's just a ton of data, and there is the need to do training in a distributed manner. So Spark NLP is great. And then in terms of runtimes for Apache Spark, you can run it anywhere, and it's what we call Spark standalone. So you can do it on your laptop if you wanted to just play around with small sets of data. You can do it on, let's say, if you have just a compute instance in the cloud. But you can also leverage runtimes such as Yarn, Mesos, and Kubernetes. So when Spark initially came out, it was actually optimized to run on top of Hadoop, which uses Yarn. But since then, you can use it with Mesos or Kubernetes. So this is some Spark code. I'll take just a brief moment to go through it. So what's happening here, it's 6 lines of code. So we create what's called a Spark session, which is just a way for your Python code to actually interact with your Spark engine. We then load in the data. So in this case, we're just pulling down a CSV file from a Google Cloud Storage bucket. We're then creating what's called a linear regression model, which is basic machine learning, but if you're able to just do it from one line of code, we then just call model.fit on your training data, and then we can print out the, in this case, the root mean squared error. So for anyone who's used scikit-learn, Apache Spark MLlib has similar functionality, just several black box models for anything that more or less isn't deep learning. But what's really nice about the code here is that apart from the import statements, which I didn't include, this is an entire working piece of software. And it doesn't matter if your cluster has 2 machines or 200 machines. It's going to be the same thing. You're going to have to write the same amount of code, and it'll do the same thing and scale underneath the hood. Spark actually used to be a little finicky with actually configuring the clusters, but newer releases have tools that are operating underneath the hood to dynamically allocate where all of your data should be going. So super nice, super easy to use. But as I mentioned, it's really great for machine learning jobs that aren't deep learning. But if you want to do deep learning, a great tool for that is to use TensorFlow. TensorFlow being an open source machine learning framework written at Google. Also has a rich ecosystem of tools. Something that's a little different from Spark and TensorFlow. TensorFlow is specifically designed for doing machine learning and deep learning, where Apache Spark is designed to do data processing, but also has a machine learning framework built on top of it. So they don't both do the exact same things, but they both do. They both have distributed machine learning capabilities. TensorFlow uses Keras as its high-level API, and I'll show you an example of that in just a moment. TensorFlow is also super easy to distribute. So in this case, there's a little bit of work involved to distribute it, but I will show you how little that actually is. And again, this was spun out of the paper that Jeff Dean was writing in 2012. TensorFlow came out in 2015, but it has actually been used internally at Google much longer than that. And TensorFlow has APIs in Python is the most popular one. Then there's also JavaScript, Swift, Java. I believe there's Go, C++, and there's also lots of APIs that are very community driven. So you can generally get started in any, in the language of your choosing. This room, I would hope that would mostly be Python. But if you wanted to play around with others, there are bindings available. So just quickly talking about some of the ecosystem that TensorFlow has. You have TensorFlow Probability, which is a library that is built on top of TensorFlow for doing more advanced statistical use cases. You have TF Agents, which is used for reinforcement learning. TF Ranking, which is used for ranking algorithms. TF Text for natural language processing. And then TF Federated for federated learning. And there's lots of others too. These are just a couple of the ones that I find to be pretty cool. And then for actually distributing your load, we have something called TensorFlow distribution strategies. The idea behind this is it's baked into the TensorFlow ecosystem, and it's designed to make machine learning distribution super easy to do. It's great for researchers, practitioners. This is being used in production use cases, and there's lots of different ways that you can actually utilize this. Provides great performance out of the box. There's just very little tuning that you need to do. It's easy to switch between different distribution strategies with very little code changes. So what do I mean by this? So here we have some sample TensorFlow.keras code, where we have a neural network that's just written in 4 lines of code, just by adding the different layers to the keras model itself. We can then compile the model and provide the optimizer, the loss function, and the metrics that we want to optimize for. And then we can fit it to our training data. But this is something I can run on just my machine, and this will work. But if I wanted to take this code and then move it into a distributed environment, all I have to do is just add the strategy. We define the strategy, and then we include it in the scope of the we include it in the scope of the code. So in this case, I'm using the mirrored strategy, which is a form of synchronous data parallelism. But there's strategies for using TPUs. There's strategies for doing, I believe there's a parameter serving strategy that's in the works. And there's lots of others. And so the idea here is if you wanted to switch between these, maybe you tried using model parallelism, you want to try using data parallelism. All you have to do is swap out the strategy here, and the rest of the code can remain the same. OK, so we'll just wrap up here with some closing thoughts, given all that we've talked about. So the key takeaways that I want everyone to, leave the room with is that the differences between data parallelism and model parallelism, the general idea here is that data parallelism is designed to distribute your training data. Model parallelism is designed to distribute your model training and your model, they're both designed for model training, but it's designed to distribute your model parameters. In terms of hardware, CPUs are generally used for what I like to say are the brains of the operations, and it's able to actually distribute the data to the different machines, where GPUs and TPUs are really good at doing the mathematical components. That's what they're designed to do. They're designed to do that parallelization. And then in terms of actually doing machine learning, Apache Spark MLlib is really good for anything that's not deep learning. TensorFlow is then good for anything that is deep learning. So there's a lot of gray area with these, but I think if you're just getting started and diving in, these are some good guidelines to stick to. So I work at Google, specifically work at Google Cloud, so I like to just mention this. So you could, of course, get started doing this stuff on your laptop or building your own machines, but what I honestly think is an easier way to do is to play around with these in the cloud if you're able to do so. So I won't spend too much time here, but Apache Spark, you can actually use a product we have called Cloud Dataproc, which is a managed Apache Spark cluster. And then for TensorFlow, you can use a product we have called AI Platform. And so these both allow you to scale up multiple machines, distribute your load, and effectively add infinite compute depending on your use case. If you're interested in learning more, so here's just a couple of interesting papers that I had actually read as just reading more about this stuff to prepare this talk. So the first one is large-scale distributed deep networks. That's by Jeff Dean's team, and this is what introduced the disbelief network. We then have deep learning with COTS HPC, which I believe stands for Continued Off-the-Shelf High-Performance Computing. That's Coates et al. And then the Apache Spark paper, I think, is also really interesting. Spark cluster computing with working sets, and that's Matej Zaharia et al. In 2014. And so that's it. I'll stick around for some questions, but yeah, thank you all for coming. How are we doing? Cool. Yes?
You don't think this split the model, what if it's like dependent on the, like a deep neural network with memory-based RNN, if you depend on the previous prediction for the next one, how do you do that?
Yeah, so that's a great, the question was, so there's a type of neural network that's called a recurrent neural network, where it's effectively, it's a network that has just a single set of parameters that you're continuously updating. That might be one example where this is really hard to do because you are relying on, you are of course relying on the different sets, or the previous output of the data. What you might be able to do, and this is just me sort of thinking up something, you might be able to replicate that model like maybe 2 or 3 times so that they might end up being slightly behind each other. But you can then maybe average the outputs of each of them or like maintain the different weight states as you're training it. That might be one way to do it. But RNNs are definitely going to be one of the models that are going to be naturally harder to do this with. And if anyone else has any ideas, like feel free to chime in. But
do you have any recommendations for tooling when you're splitting across machines and you have failures, logging, and trying to find where stuff went wrong, like training log multiple days,
yeah. So there's 2 pieces of tech. One that's more closely related to TensorFlow, the other with Spark, that I would recommend checking out. The first one is something called Kubeflow. So this is actually distributed TensorFlow on top of Kubernetes. And so that manages a lot of that for you in terms of the logging and the and just different, different metrics and information that you might need for debugging this stuff.
How do you spell that?
K, I can type it here. So it's
The translator has it.
oh, okay, I could just type it here too. So Kubeflow. So we have Kubeflow, which is really good for TensorFlow on Kubernetes. And then there's also TensorFlow Extended is another tool that you can log that stuff with TensorFlow. But if you're using Spark, and I believe you could also do this with TensorFlow as well. MLflow is a really good piece of technology for those sorts of things.
as the logging?
Yeah. So something that I just, in the interest of time, did omit from this talk is actually building this out end to end. That could be an entire separate talk on its own, so maybe next year. But yeah, there's a lot of work involved to actually distributing these and getting them into a production environment. Some of the managed pieces of tech like Dataproc and AI Platform do a lot of this for you. But if you are building your own, if you are going to build out your own cluster, there is definitely work there involved using some of these open source tools.
Sorry, will you be able to share this your presentation? Will you share that like your Twitter or something, or is that closed?
I think I can. I know the worst case this will be posted on YouTube eventually. But I will look into that for you. Yeah, right there.
You mentioned that like Spark kind of handles the details of like how it distributes things across different nodes. Imagine if you just like load that up on the computer, if you have like a node of computers, do you have to tell it something, I'm guessing, in order to like detect what options it has, or does it, how much does it actually do on its own?
Sure. So my understanding of how that works is that if you're able to connect all the computers together, this part is definitely, like doing the physical hardware manifestation is definitely outside of my wheelhouse. My understanding of how that works is that if you have a cluster that is configurable just in terms of, I think, just in the same network, you can then provide each of the IPs of each of the machines into Spark, and then it can actually find those, and assuming it has read and write access to the machines, it can then optimize them and include them as part of the cluster. Cool.
I have a question about asynchronous data parallelism that you talked So what's the advantage of doing it asynchronous? I'm just trying to understand, right? Because I cannot take it the face value until it's complete, so whether it's synchronous or asynchronous. I mean, with asynchronous I can go away and do something and then it comes back, but other than that, the work is not clear until it's actually completed.
Sure. So let me go back to the slides here. So the question was just like more along the lines of like the advantages of doing asynchronous versus synchronous. So if you're using synchronous data parallelism, the work gets processed in cycles. So let's say each one of these workers might process 100 rows of data. But before it updates before each worker updates each other with the results of the work, it cannot start. It has to wait for the last machine to finish its 100th row.
But that's not the standard processing even in HDFS, right? I mean, the Cloud platform, that's not how it works.
So nowadays we've moved more towards doing asynchronous just because this is in most cases going to be strictly better. It does require an extra piece of hardware that's maintaining the parameters, but the idea is the workers can then each move as quickly as possible, and in most cases you'll see that there'll be speed ups here. There is potentially the problem where because this relies on I/O to the parameter server, this could end up being slightly slower for smaller models, but in almost any realistic use case, this is going to be strictly faster. So this is really where you want to be landing if you're going to end up breaking into this stuff.
Thank you.
Yeah, you got it.
I don't know if you saw the previous talk, but the speaker talked about Dask, which is similar. It helps you do parallel computing, but it's kind of pure Python. And I was wondering if you had any experience with it, or if you ever explored it, or just looked at it, if you have thoughts on it, or if Google has thoughts on it, anything.
Sure. I believe that uses Arrow underneath the hood, I want to say. So Dask is, so the short answer to your question is I'm not overly familiar and I haven't spent a whole lot of time with it. I have tangentially heard of it and it seems like a super interesting project that I do want to spend time in because it's doing this. But yeah, it seems like a really awesome piece of technology, and I think there's a lot of work, especially being done, I want to say with pandas, to integrate functionality of Dask so that you can get more speed advantages using just pure Python parallelization. But yeah, I definitely want to look into it, and I'm super excited to see where it goes. Anyone? Yes?
So, like, I like most people, practice on a laptop.
Yeah.
That's not connected to the cloud. Sometimes I won't be near internet, or the internet will be spotty.
Totally.
Do you like where's your eye looking at as far as like personal computers go?
Sure. Ooh, that's an interesting question.
What computers should I want to get?
Yeah. So I mean, there's always going to be a need for doing this stuff on your laptop, in my opinion, because even though Wi-Fi and internet is becoming more and more accessible, there's just always going to be cases where it's not available. Something that I do think is really cool is using like notebooks in the cloud, or using like Google Colab, which is a free notebook that you can use.
Just read one, just to play it.
Oh, cool. Yeah.
While you're talking.
Yeah, that's awesome. Colab's really cool, but I think notebooks are always going to be important. They're definitely the part of programming that I spend most of my time in. Jupyter notebooks to me are absolutely incredible pieces of tech. Colab is too, but I definitely generally use Jupyter more just based on what I've used in the past. So there's always going to be a need for that. I know there's also, there's initiatives being worked on where you can kick off jobs, like you can kick off distributed jobs from notebooks, which I think is really cool and also allows you to take advantage of maybe part of your cluster, if not the entire thing. If you want to just work on some smaller like toy examples, or like if you have a cluster that's maybe that has 400 machines and you expect your job to utilize most of those, you might be able to kick off a small job from a notebook that might use only 4 of those machines. That'll just take less time and give you some early results to see if what you're working on actually makes sense. So I don't know if that answered your question, but sure. Yeah. So the TLDR is that, there will always be a need for notebooks. There will always be a need to like do some of this work on your computer, just because you don't have to rely on the internet and things like that. So I would definitely always have a laptop. I'm personally a fan of laptops, but to each their own. So. Anyone else? Cool. Well, I'll be around. Feel free to come up if you have any questions. Thank you for coming.